Hello, welcome back. In the last video, we covered the OSI and TCP models, and that will be the episode 1 of my videos. Now it's gonna be episode 2, the frameworks that explain how data moves through a network. Today we're getting more hands-on, and we are covering 3 things: network topologies, the physical and logical layouts of networks, the key devices that powers every network, routers, switches, firewalls, and more. The IP addresses, how the device finds each other, including public versus private, static versus dynamic, and the difference between IPv4 and IPv6. By the end, you'll understand how networks are usually built and configured. Now let's drop in. Now we're gonna talk about topology. Let's start with simple. Point to point, exactly what it sounds like. A direct connection between two devices. One cable, two ends, no middleman. Think of two computers connected directly, or at least line between two office buildings. It's fast, it's dedicated, there's no contention, no collision, but it doesn't scale. You can't connect hundreds of devices this way. You can see point-to-point links, one connection, VPN tunnels, and sometimes data center interconnects. It's the simplest topology. Everything else builds on it. Now we're gonna talk about the bus topology. Bus topology connects all devices to a single thread cable. The backbone, a device sends a signal and it travels down to the whole cable. Every device sees it, but only the intended recipient processes it. The rest is ignored. It's cheap and easy to set up, but it has major flaws. One device can transmit at a time, or you get collision. If the backbone cable breaks, the entire network goes down. Troubleshooting is painful because the problem could be anywhere along the line. Bus topology were common in early internet networks. Today, you'll almost never see them. We have moved to the better design. And the next topology is the ring topology. In a ring topology, devices are connected in a closed loop. Data travels in one direction around the ring, device A to B to C, and back to A. Some rings use two counter-rotating rings for redundancy. If one fails, traffic shifts to the other. Historically, token passing controlled which device controlled transmit. A token circled the ring, and the only devices holding the token could send data. This eliminated collision but added complexity. Ring topology is still used to some metro networks, industrial control system, and older fiber distributed data interface network. For most modern LANs, it's been replaced. Now we're going to talk about star topology. This is the most common topology today. Your home and your office network almost certainly use it. Every device connects to a central switch. Your laptop plugs to the switch. The printer plugs in the switch. Nothing connects directly to another device. The benefits are huge. If one cable fails, only the device loses connection. The rest of the network stays up. Adding or removing devices is simple. Troubleshooting is straightforward, and the downside, central switch is a single point of failure. If it dies, everything goes down. But switches are reliable, and you can add redundancy. Star topology, sometimes with multiple switches interconnected, is the foundation of modern Internet LANs. And we're gonna talk about the mesh topology and full mesh versus partial mesh. Mesh topology is about redundancy. Every device connects to multiple other devices, creating multiple paths between any points. And full mesh, every single device connects directly to every other device. The math grows fast. In device needs times in minus divided by 2 connection with just 10 devices. That's 45 cables. Full mesh, incredibly resilient. A single failure won't disconnect anything, but the cost and complexity are enormous. You will find full mesh in one backbone and critical infrastructure. Partial mesh is more practical. Some devices have multiple paths, but not all. This balances redundancy with cost. Wide area networks and data centers use partial mesh extensively, providing backup paths without the full cost of interconnectivity. Now we're going to talk about tree topology. Tree topology combines star and bus. It's hierarchy. At the top, you have the core of a root switch, branches extend down to intermediate switch, and leaves at the bottom are ends devices. Data flows up and down the tree structure. This is scalable. You can add branches as the network grows. It's easy to manage. Each branch can manage separately, but the root switch is critical. If it fails, large segments collapse. Tree topology is common campus networks, large enterprise, local area networks where you need organized hierarchical expansion. Now we're going to talk about hybrid topology. Real-world networks really use just one topology. Hybrid topology combines two or more. You might have started at the department level, connected by ring backbone between buildings with a partial mesh linking data centers. This gives you the best of everything. Simplicity of star, the redundancy of mesh, the scalability of tree. Every large network is essential a hybrid. Understanding the basic topology helps you recognize them a hybrid design, and that's what's matter for troubleshooting. Now we're gonna talk about key networking devices. The actual hardware that make those topologies work. Over the next few slides will cover 6 essential devices: routers, switches, servers, wireless controllers, access points, and firewall. Each has a specific role, and knowing what each device does and what OSI layer operates at is the fundamental to building and fixing networks. Now we're going to talk about routers, connecting networks together. A router connects different networks. Your home router connects your local area network to your ISP network, which connects to the internet. Routers operate at layer 3 of the OSI model, the network layer. They read IP address and make the forwarding decision based on routing tables. Routers use protocols like OSPF, EIGRP, and BGP to learn routers and find the best path. Your home routers also does NAT, network address translation, allowing all your private IP devices to share one public address IP. It assigns IP address via DHCP without routers internet will exist. There's be no way to move data between separate networks. Now we're going to talk about switch, forwarding data within a network. A switch connects devices within the same network. Your laptop, printer, desktop all plug into a switch. Switches operate at layer 2, the data link layer. They learn MAC address and forward frames only to the correct port. Unlike old hubs, which broadcast everything to everyone, a switch creates direct logical connection between senders and receiver. This means full duplex communication and no collisions. Manage switches and add VLAN support, allowing to segment and physical switch into multiple logical networks. Spanning tree protocols prevent loops, which are the backbone for every local area network. Now we're gonna talk about hosting application service, server. Server provides services to the other devices on the network. A file server stores documents, a web server hosts websites, a database server handles queries, a DHCP server assigns IP address, a DNS server translates domain name. Server can be physical machine in the data center, virtually machine running to a hypervisor, or cloud instance. They typically run operating system designed for uptime and service delivery. Servers don't initiate connection, they listen and respond. In the client-server model, your device is the client and the server provides what is requested. Now we're gonna talk about wireless controls, access point, and firewall. Three more critical devices. As an essential point, bridges a wireless device to the wired network. It broadcasts a Wi-Fi signal that your phone and laptop connects to. Access point Access point operates at layer 2 and forward frames between wireless clients and the switches they plug into. A wireless controller manages multiple access points from simple interface in the large offices, hotels, or campuses. You might have dozens of access points. The controller handles configuration, channel assignment, power level, and seamless roaming so users don't drop when moving between a power controller. What traffic is allowed in the out network. It operates across multiple OSI layers, filtering traffic based on rules. Firewalls can be hardware appliance software running on a server or a cloud base. They are the first line of defense, permitting legitimate traffic and blocking threats. Now we're gonna talk about the 4 types of IP addresses. Now IP addresses. There are 4 types you need to know: public, private, static, and dynamic. A public address is globally unique and routable on the internet. Your ISP assigns one to your router. When you visit a website, that's the site you see public IP. The public address must be registered and can't be duplicated. A private IP address is used inside your LAN. These addresses are not routable on the internet. The private regions are 10.0.0.0 to 10.255.255.255, 172.16.0.0 to 172.31.255.255, and 192.168.0.0 to 192.168.255.255. Every home network uses this. A static IP address is manually configured and never changes. Server printers and network devices often use static IP because they need a consistent address so that other devices can always find. A dynamic IP address is assigned automatically from pool by a DHCP server. Your laptop usually gets dynamic IP. It might change over time, but the most client devices, that's perfectly fine. Now we can talk about data measurement units, binary notation, and subnetting. IP addresses are just numbers. They are binary underneath. An IPv4 addresses like 192.168.100.10 breaks into 4 octets. Each octet is 8 bits. 1 and 2 in binary is 111.0000000. That 168 is 101010000. 100 is 011000100. 10 is 0000110. 32 bits total. The subnet mask is 255.255.255. Separate the network portion from host portion. 255. And binary is all ones. 11111111. Those are marked that network part. The zeros mark the host part. So in 192.168.100.10 with mask of 255.255.250, the first 3 octets identifies the network, and the last octet identifies the specific device. Quick data units: a bit is a single 1 or 0. A byte is 8 bits. A kilobyte is roughly 1,000 bytes. A megabyte is roughly 1,000,000 bytes. A gigabyte is roughly 1,000,000,000 bytes. Network speed are measured in bits per second. Megabytes per second, gigabytes per second. Don't confuse bytes and bits. Now we're going to talk about IPv4 versus IPv6. IPv4 versus IPv4 is a 32-bit addresses. That gives us about 4.3 billion possible addresses when the internet was designed. That seemed likely plenty. It wasn't. We have been out of new IP addresses for years. IPv6 used 1 to 128 bits. That's astronomically large address space. 340 decillion addresses, enough to assign unique address to every atom of the Earth. IPv4 addresses looks like 192.168.1.1. Addresses look like this. IPv6 address looks like this. FA8094DB 946E 8D4A 129E. They are written hereditary separated by colons. Shorthand rules let you comprises consecutive zeros with double colon. IPv6 also bakes in security. IPsec is mandatory, not optional. Auto configuration lets devices assign themselves addresses without needing DHCP, though DHCP v6 still exists. The sensation is slow but ongoing. Every modern operating system and device supports them both. As a network professional, you need to understand both. So that's network topologies: point-to-point, bus, ring, star, mesh, tree, and hybrid. The key devices: routers, switches, servers, access point controls, and firewalls. And IP addressing: public versus private, static versus dynamic, and subnetting basics, and IPv4 versus IPv6. These are the building blocks in the these are the building blocks. In the next video, we'll start putting all together with real-world configuration and troubleshooting. Thanks for watching, and any question in the comments, and we'll see you in the next time.